This video will cover the Compact Electrical Temperature Controller Capstone project for the Instrumentation program at Oklahoma State University Institute of Technology. This capstone project was done for the spring semester of 2019 by team members Cliff Adams, Logan Mcgowin, Eric Ringgold, and Jesus Rivera. The purpose for this project is to be able to heat up or cool down the temperature of the process fluid inside this 8-gallon tub. The tub itself is insulated by polyurethane and is encased in plywood. The way that the process fluid is heated up or cooled down is with the use of one of these heat exchangers. As the process fluid passes through the heat exchanger, heat is either absorbed or removed from the process fluid. Here you see a picture of the way the PN material is connected inside a Peltier pad. As you can see, they are connected in series together. This is so that the current is constant within the Peltier pad. This is a side view of the Peltier pad. When the current flows N to P, it creates a cold junction. This is because electrons are being removed from the surrounding surface. When current flows P to N, it creates a hot junction. The electrons that were removed from the cold junction are dispersed to the hot junction. This is a diagram of the heat exchanger system in our project. Number 1 indicates the radiator section where heat is either dissipated from the system or added to the system. The magenta blocks marked with number 2 are the heat exchangers. 2 of these heat exchangers circulate radiator fluid. The middle heat exchanger circulates the process fluid. In between these heat exchangers are our Peltier pads. In cooling mode, they are used to move heat from the middle heat exchanger to the outside heat exchangers. In heating mode, they move heat from the outside heat exchangers to the middle of the heat exchangers. The proportional valves, number 4, are used to control the amount of process fluid sent through the heat exchangers. The stream from each process valve then reunite at the outlet and are fed back into our tank. We used 14 relays in our project. 2 were used to turn the pumps on and off, 4 were used to turn the Peltier arrays on and off, and 8 to control the flow of current through the Peltiers. These 2 bus bars are a single array used to control the mode of our Peltiers. The Peltiers are split up into 4 arrays. 3 of the arrays have 3 Peltiers each, while the final array only has 1 Peltier. The mode is controlled by the relays below that allow the current to flow from either yellow to blue or blue to yellow. This creates a situation where both sides of the Peltiers can be either heating or cooling. All relays have their own white and black wires. These 2 wires are for the signal that comes from the compact Rio controlled by LabVIEW and allows for the relays to switch. This side of our project contains our 4 power supplies. Each power supply is able to deliver up to 30 amps at 12 volts. The relatively high amperage was necessary as each of our Peltiers is rated to draw up to 10 amps of current. This meant that we had to split the Peltiers up into 4 arrays, each of which had to draw less than 30 amps. 3 of the power supplies contain their own 3 Peltier arrays. The 4th power supply energizes the final Peltier along with the proportional valves, compact Rio, and pumps. These are our radiators. We use 2 blade and fin radiators. Air is forced around radiator fluid that is flowing through the small fins. This contact with the air forces heat to be exchanged between the ambient air and our radiator fluid. This is the outside of the radiators. We used 8 fans to force air through our radiators. These reservoirs contain the radiator fluid. The glass housing on each allows them to tolerate our maximum attainable temperature. Our system contains 2 completely separate radiator circuits, each with its own pump, radiator, reservoir, and 4 fans. These are the proportional valves. One controls the flow around the heat exchanger, named the bypass valve, while the other controls the flow through the heat exchanger, named the exchanger valve. These valves use a 2 to 10 volt control signal. This means that the valve will open proportionally to the voltage sent to them. A 2 volt signal would tell the valve to close, 10 volts would be fully open, and 6 volts would be half open. Our project featured 3 RTDs to monitor the temperature. The process fluid inside the tank was monitored by this 4-wire RTD. The return from the heat exchanger was monitored here by a 3-wire RTD. Finally, a 3-wire RTD also monitored the radiator from inside of this reservoir. National Instruments Compact Rail was the controller used in this project. It was programmed via LabVIEW 2017. The project used 3 cards for the controller. First, the NI9474 is a digital output card that is able to switch outputs. It allowed us to send the required 12-volt signal to control our relays. Next, the NI9263 is an analog output card. It is used to send the 2 to 10 volts control signal for our valves. Finally, the NI9219 card is used to read the signals from our RTDs, monitoring temperature. Once the project is running, you see the tank temperature, return temperature, and radiator temperature are being reported in real time. They are reported in Celsius on the top of the window and Fahrenheit on the bottom. Manual control is operated by the switch in the manual control section. Once powered on, the user is able to control the pumps in the system. Once the pumps are running, the user is able to power on the Peltier pads to begin controlling the temperature. The Peltier polarity switch toggles the 2 modes in the system, heating and cooling. In this case, the red indicates the system is in heating mode. The slider bar next to these buttons control the proportional valves. Manipulating the percentage bypass slider adjusts how much of the flow bypasses the heat exchanger. The exchanger valve then automatically adjusts itself accordingly so that the total flow is not impeded. The process monitor reports systems variables in real time. The thin blue line represents the change made in the percentage of flow passing through the heat exchanger. This is reported as a number between 0 and 50 so that the full range is visible on this graph. The orange line represents the temperature of the process fluid after it exits the heat exchanger but before entering the tank. As can be seen here, it is responding to the system being in heating mode. The red line is the process variable. It is the temperature of the process fluid inside of the tank. Each variable is also reported on the side of the graph in the digital indicator. When manual control is switched off, the pumps and peltiers all de-energize and controls are disabled. In timed on-off mode, the set point determines the behavior of the system. In this mode, the pumps remain on constantly. If the process variable is within the deadband of the set point, the system will automatically adjust the valves so that 80% of the flow bypasses the heat exchanger. This prevents the temperature of the radiator circuits from having a big impact on the process fluid. When the set point is above the process variable, the system will switch to heating mode. The proportional valves will be adjusted so that 100% of the flow is sent through the heat exchanger. When the set point is below the process variable, the system will switch to cooling mode. Again, the valves will send all of the flow through the heat exchanger. The deadband is adjustable so that the tolerance range around the set point can be made bigger or smaller. The wait time for the system can also be adjusted. This is the time the system waits before checking if changes need to be made. Here, every 5 seconds, the VI checks whether it should be heating, cooling, or off. Large wait times can cause overshoot, but can also reduce on-off oscillation. The process monitor in RVI is useful for real-time analysis, but it only displays up to 10 minutes of data. For this reason, a separate VI, write to file, can be used to record data in a separate file. Once the VI is open, it is necessary to select a file before running it. In this case, the file sudv9000. It is important to ensure that the file doesn't contain other data, so I will clear the contents and save the file empty. Now the main VI running, I can run the write to file VI. As can be seen, the values from the main VI are sent here. The values are recorded to the selected file every 10 seconds. This delay ensures that hours of data can be recorded without the file being too large. So now that the VI has ran for a few seconds, I'll go ahead and stop it. then open up the file. Here we can see that 3 data points were recorded. It is now possible to transfer this data into Microsoft Excel and plot a process curve. I'll go ahead and open a previous process curve to demonstrate. In this process curve, 3 of the 6 columns of data are reported. This has been an overview of Team 1's Capstone project at Oklahoma State University Institute of Technology for the spring semester of 2019. Hope you enjoyed our video, and thank you for watching.